Okay, so we've been learning about these gas laws and these gas relationships, and this is where we've kind of ended up. You should be able to understand this. You have some first measurement, first set of pressure, volume, amount, number of moles, and that's at some temperature. Okay. Um, if any of these variables change, or if all of these variables change, this is the equation you can use. This is the mathematical relationship. Pressure and volume are inverse. Pressure, and they're both, pressure and volume are directly related to amount and temperature. Okay, and so we can set these um, first variables and compare them to some second set of variables, and we should be able to calculate the change. It gets kind of complicated because you have to make, this is 5 different measurements that have to be taken or known, right? And so what we do is we use what's called the ideal gas law to simplify this, okay? And so what we do is we kind of ignore this second set of variables, okay? And we say, well, let's imagine that we are measuring these variables at not a first, but an only. So let's just say we're measuring that some pressure, volume, amount, and temperature. And so what we use is we use the standards that we've been learning. We know that standard pressure um, is can be many different units, can be many different measurements. Um, they would include ones we've been using so far. Would include, of course, kilopascals, kPa, right? This would include torr, or millimeters of mercury, same thing. This would include atmospheres, ATMs, PSI, ones we've been using. There are some other ones as well, but these are the most commonly used. Just a reminder, what a Pascal is, or kilopascal would be 1,000 pascals, and of course a Pascal, going back to connecting this to building of these units, is of course a Newton per square meter, right? That's a Pascal. Okay, so this would be 1,000 newtons per square meters. So these are at sea level on an average day. You can have these standards for, just give myself a little more room here. For kilopascal, that standard is 101.325. Probably might have these memorized. At torr, 760.0. Right? Atmospheres is 1.000. At psi, it is 14.7. Okay, remember that's pounds per square inch. Okay, the atmospheres, of course, we invented to simplify all of these, so we don't have to use these weird numbers. Just one. So those are all the standards. Get those on the equation sheet. So if we can take these and set these all to standards, right? And then we know, of course, standard temperature is 0 degrees Celsius, or 273.15 Kelvin. That's standard temperature. Okay. Standard number of moles, we keep this simple, is just 1 mole. If you just have 1 mole, which of course is equal to a very large number. If you had a mole of helium atoms, that would be 6.022 times 10 to the 23rd atoms, particles of things, right? Atoms of helium, if you were talking about helium. That's what that'd be equal to 1 mole. That's that amount. Okay, it's a big number, but because atoms are so small, you can fit that in. Now, at standard pressure, temperature, and moles, it turns out that every gas, no matter what, has the same volume at all these standards. And so we can actually get the standard volume as well, okay? And the standard volume is this number that is 22.414 liters. Any volume at standard pressure at 1 mole at 0 degrees Celsius has this volume. Okay, and so this is the standard volume that we use. We can measure this out. It's amazing that no matter what, if it's atoms of helium, if it's oxygen molecules, oxygen doesn't really exist as, any gas will have this volume. Okay, no matter the size, the mass, if it's diatomic, anything. Any volume of gas, 1 mole of it will have this volume, and that's standard. Okay, and this has been measured and calculated out in. I'm not sure if this is on your equation sheet. I'll have to double check that. I'm gonna write that down, but that's standard. Okay, that's the standard volume. Okay, so what we do is we simplify this. We take each of these. We take each of these standards. Okay, here's standard volume, standard temperature, standard moles. And of course, we can take any of the standard pressures, and what we do is we get and use a constant. Okay, so that if we multiply these, we know that at all these standards, we can always get the same number. As long as you have a gas under a certain pressure, certain volume, certain number of moles, all standard, temperature, we can get a constant. Okay. A lot of times in science and math, we abbreviate constant as a lowercase k. Okay. If we're talking about lowercase k, we're talking about the ideal gas, or we're talking about gas laws, we use an abbreviation. We use a symbol. Instead of K, we use capital R. Okay. That just means this is the symbol for the gas constant. So that no matter what this relationship is, we can multiply these all together and get this constant. Okay, and so what we do is we use this to simplify these equations that we've been using. This would be kind of similar to the combined gas law, or this would be a combination of all of them together, all of these 4 relationships together. Okay, and so we get this gas constant. Okay, and so every standard unit of pressure would be a different number, different numeric value with a different unit. Okay, so you can plug this in here. So what you're going to do first is you're going to, on that worksheet, is you're going to calculate the R value for these different pressures. Okay, so if we take standard pressure, okay, let's say we're doing kilopascals first, 101.325 kilopascals. Okay, that's our standard, and we're going to multiply that by the standard unit of volume. We're going to divide that by the standard number of moles. We're going to divide that by the standard temperature. Okay, so if we take this standard pressure in kilopascals, multiply it by the standard unit of volume, which we said was 22.414 liters. Okay, and then divide by, so that would be our standard volume, and divide by the standard number of moles. So that would be 1 mole, 1.000 moles. Okay, and divide by the standard temperature or the standard unit of temperature, which is Kelvin, 273.15 Kelvin. Okay, if we plug these numbers in, we set that equal to this constant. We can get this constant, this R. Okay, we can get this gas constant, and we can use that to simplify this equation. Okay, so we take out the trusty calculator here and plug these values in. Oops. A little smaller. Plug these values in here. So if we take 101.325 and multiply that by 22.414 pretty sure that's there. And divide that by 1. I'm not even plug that in, and divide that by 273.15. Reiterating the fact that the temperature has to be in Kelvin, cannot be in Celsius or Fahrenheit to get this absolute scale. Okay, and so that gives us a value of 8.31. So if we have 6 significant digits with our pressure, 5, 6, 1, 2, 3, 4, 5 in our volume, 1, 2, 3, 4, it's exactly 1, 5 in our number of moles and 5 in our temperature, round that to that many significant digits. The R value, anytime you use kilopascals, R is always going to be, this is constant, doesn't change, 8.314 5. 7 there. Okay, and the unit of this constant, this is why constants always have weird units, is to cancel this out. So we can use these variables without having a second set. Okay, you notice the ideal gas equation. So the unit of this would be a kilopascal times a liter per mole Kelvin. Okay, or what I like to say is a kPa per molk. So the gas constant for kilopascals is 8.3145 kPa per molk. And so why would this be useful? Okay, what would be useful for this? What we do is we can use this as to simplify all these relationships, simplify these equations that we've been using. Okay, I'm just going to shrink that down there. All right, and so what we get is if we know we have this pressure, okay, and we know that if we have pressure, we multiply that by the volume, we divide that by the number of moles, we divide that by the temperature. We know these are all equal to R, okay? And what we have here is we have a fraction, okay? And what scientists sometimes don't, sometimes they like fractions, sometimes they don't. But if we take this out of fraction form, okay, multiplying both sides by number of moles, multiply both sides by N, multiply both sides by T, canceling it on the bottom there. Okay, what we get is PV is equal to, and the order we usually do this in is nRT, doesn't matter the order, okay? And so this gives us the equation that's known as the ideal gas law equation, okay? And so now, instead of having this equal to some second set of variables where you have to have P1, V1, mole 1, so you have to take basically 5 measurements to get that 6th unknown. What we do is simplify that and just use this equation so that all we have to do is measure pressure, volume, right, and temperature. Measure 3 things and you can always get that 4th thing. The R never changes, okay? And so what you're going to do on that worksheet is you're going to calculate the R's for if this standard pressure used was torr or psi or atmospheres. So you're going to get different R's for all of them. Okay, and so you can use this equation if you know that if you know the pressure is measured in kilopascals or wants the pressure in kilopascals, right? Then you would plug this into R always. It's a constant, never changes. And so then all you have to do is measure the volume, the moles, and the temperature, right? So if it was asked for pressure, right, you would use N, what measure the number of moles, plug in 8.3145, measure the temperature, divide by that volume that you have, and you would be able to calculate the pressure of that gas. So it simplifies and makes things a lot easier. It's called the ideal gas law, ideal gas constant, and this PV equals nRT, or often known as PIV-NERT to memorize it. PIV-NERT is the ideal gas law. One of my favorite equations. This is a great connection between physics and chemistry. Okay, so try to find those R's and use this equation for those first 4 problems. Good luck. Enjoy.